Hi everybody, I just wanted to put together a quick video here to show you how the C code that you were programming in Lab 6 connects with the assembly programming that we've been talking about lately, and in particular the RISC-V architecture. So I've opened up the Lab 6 file here. You can see the linear algebra file with all the functions implemented, and in our main function we create a bunch of test vectors and then we run through a small program here to check that our functions are working properly. So if we go ahead and start a debugging session here, we'll build and start to run, and the debugger will dump us at the entrance to our main function. And when you were debugging your Lab 6, you probably used the debugger here to step through the different lines of code and see what the corresponding variables, the way they changed, to be able to check that your code was working properly. But now that you know about the RISC-V assembly language, you know that these lines of C code are actually translated into assembly instructions. And if we want to actually see what the compiler and assembler have done to actually put the instructions onto the RISC-V architecture, we can click these, look in the Disassembly tab here, and if we click this Switch to Assembly button here, it'll switch us to the view where we're looking at the assembly instructions. And so you'll notice here that we can find the instruction that's currently operating here. So we see add immediate, and we're just going to store a value into A2 offset from the stack pointer, and you'll notice the machine code here. One thing to note here is normally our instructions are all 32 bits. Those are the ones that we've talked about. But we also remember when we looked at jump and link and branch, we talked about how we store only, we leave off the least significant bit of our jumping, our relative jumping addresses, because we never need to jump a byte, but we don't get rid of the second least significant bit because we want to maintain the ability to jump on 2-byte boundaries. And the reason for that here becomes apparent because we have these compressed instructions. And so you'll notice that these instructions here for add immediate, this doesn't map onto a full 32-bit number, but there's actually a subset of compressed instructions which allow you to represent this whole add immediate instruction in only 16 bits, in 2 bytes, as opposed to using a full 32-bit number. And so what this allows you to do is it allows you to save memory. And so you can store 2 instructions for the same memory cost as 1, which becomes valuable. So you can check out the instruction set architecture and look at the compressed extension, the C extension, to see these instructions and how they're encoded. There's some limitations in terms of the different registers that you can actually access and use and how big of an immediate you can encode, but that's another kind of neat thing to check out. Another thing I just want to point out here is that when you are actually building your function, you'll notice that the labels are gone and those get replaced with physical memory addresses. So for example, here we're calling the dot product function, and here we're using jump and link, and then we're jumping and linking to a particular memory location here. And let's say if we want to try to find where this memory location is here, we could try to scroll on the left-hand side to find that. But an easier way to be able to do that, in the disassembly, actually doesn't allow us to scroll all the way through all the memory addresses. It only loads a small subset of it. So if we want to see what's going on inside this dot product function, what we can do is we can click this disassemble function here. If we click disassemble function and then type in dot product and then hit enter, what it's going to do is it's going to jump into that dot product function. And so you can see the kind of main pieces that you've seen in the lectures and in your homework that you're working on, where first thing we're going to do is allocate some space on the stack and then save some registers onto the stack. And then when we get down to the end of our dot product function, we're going to undo that when we go here and we push our values, or pop our values back off the stack and into the registers using load word instructions. So I hope this has been just a little helpful way for you to see how the C code that you wrote actually gets put into the assembly instructions and the machine code, and you can really see the really nice tight integration between the C code that you write and then all of the architecture and now the microarchitecture that we've been discussing. And so I hope that you've enjoyed this kind of piece here of really seeing one of the beautiful pieces of E85, which is how everything really synergistically plays together and makes sense. and really forms this kind of beautiful, you get this really full, nice understanding of a whole stack of technology. All right.